Okay, so we're going to leave mirrors behind for a while. We're still going to talk about light rays and we're still going to draw light rays. But instead of light rays reflecting off of mirrored surfaces, we're going to talk about light rays that just pass through transparent lenses. And we need to think about things like how do distant planets and things that are so far off, or things under a microscope that are so tiny you can't see them with just your naked eye, how do things like lenses make those objects appear larger? It can still be resolved by drawing ray diagrams. Light from distant objects they hit the lens and they are actually bent by the lens before they come into your eye, and your brain can trace those bent light rays back to where they thought the object was. And in many cases, depending on the type of lens, convex or concave, just like mirrors can be convex or concave, your mind can trace it back to where it thinks the object was. And it thinks it's a much closer object. It's really just kind of tricking your mind. But in order to think about how lenses actually bend light, to go back to what light is and remember that light is a wave. And the classical little sinuous wave, but we don't want to look at it as just the side view. We want to think about the wave as not two-dimensional, but as a three-dimensional object. These are like waves you've seen in water or something, where they have a wave front. If we were to look down on this wave, we would see these linear wave crests passing by us. And that's what we need to think about, that it's a three-dimensional object, not just a two-dimensional drawing. So as light comes from one medium, like air, here in the top of this image, and passes into glass, like a glass lens, it's traveling about 300 million meters per second in air. But you can see by the black lines here, these are the tops of the wave fronts. And as the waves just start to enter the glass actually absorbs the light momentarily and slows it down. So it was going 300 million meters per second. In normal glass, it slows down to about 250 million meters per second. Still terribly fast, but significantly slower. But just because this one end of the wave hits the glass, the whole wave doesn't slow down. Just that part slows down. Because the light hits the lens or the glass at an angle, part of the wave slows down, while this part that's still in the air is still going faster. So the light wave actually bends as it's passing into the medium. And it's this bending that focuses the light through the lens onto your eye and allows your brain to form an image. And this bending of the light we call refraction. And most telescopes, older telescopes, and you can still buy them today, that have lenses are called refraction telescopes because they're slowing down and bending or refracting the light. Most of the really nice telescopes in modern times are reflecting telescopes, so they have mirrors. Let's talk a little bit about just a little anatomy of refraction. You're going to do a lab today where you're going to see these angles and have to measure them, do a little graphing, and find the index of refraction, how much the light slows down. And so we'll have, just like we were drawing ray diagrams on mirrors, we will have an incoming incident ray of light, and we will measure the incident angle from the normal to that ray of light. And it's incident, in this case, on this blue square here. It can be water or glass or plastic or diamond or any transparent material. Once the light enters at an angle, it slows down on just one side of the wavelength and bends and wheels around a corner. And then you can measure R, the refracted angle, also from the normal into this refracted ray. And that light ray then becomes incident on the bottom of the blue square where it's about to leave this medium and go back into the air. So it's going to speed up as it starts to come out of this blue medium, and it's going to bend back. And it turns out that whatever angle it came in at, ultimately when it leaves the material, it's going to be bent back parallel to the incoming ray. Okay, and we can use something called Snell law to calculate the incident of refraction, lowercase n. And it's just sine of the incoming ray over sine of the refracted ray. We can also do this graphically, and you'll do that. You'll get n from the slope of the line by graphing sine of I over sine of r and taking the slope. And the higher the n means the more light slows down and the more it is bent. So a higher refractive index means that the material is more dense and slows down and bends the light more. Like diamond has a refractive index of about 2.5, so it significantly slows light down. Air has a very small index of refraction, and it slows light down from about 300 million meters per second down to about 299.5 million meters per second. Air is much less dense. It has a lower n value, so it slows light down more. Since we're doing sine, I just wanted to see if you guys remember what sine actually means. On a circle, we're talking about angles and light being bent and angles and light reflecting and refracting through angles. So sine it's just the ratio of the circumference of a circle to the diameter of a circle. So the circumference over the diameter means there are 3.14159 diameters in the circumference of any circle. So that's the source of the sine in this calculation. So now we're going to do our lab. We're going to measure how much light bends in a certain medium, and in this case a plastic plate. So we're going to have that light from air incident on the side of a glass plate. It's going to slow down and bend as it enters the medium. As it exits the medium, it's going to speed up and bend back parallel again with the incoming ray, and we are going to measure that refracted angle from the normal. So for this lab, I've already done all of I've run the laser light through. You just simply need to read the refracted angle in the plastic. So you can start taking down the notes. All you need to record right now are the incident angle and the refracted angle, and then you can transform it into the data table on the lab on your iPad and finish out the lab. So if you see here, we have an incident angle of 0. And this should kind of make sense that it doesn't bend the light because the entire light wave hits the plastic at the same time, so it slows down at the same time and then speeds up at the same time, leaving the plastic medium. So the incident angle is 0 with the normal, and the refracted angle is 0. And I'll just now run through the slides. You'll do the measuring yourself. Like here, we have an incident angle of 10 degrees, and you can see it's 10 degrees when it comes out of the ray, and it's about 9 degrees when it's inside here. So it's incident angle of 10 and a refracted angle of 9. Here it's an incident of 20, comes out at 20 also, and the refracted ray looks like it's about 16 and a half. And I'll just be quiet now and I'll run through the slides, and you can record up to 70 degrees for the high incident angle. You can record the rest of the angles.